Mathematical complexities of string field theory in physics is a cutting-edge area of research that has been the focus of intense study by some of the brightest minds in physics. String theory is a theoretical framework used to explain the nature of particles in the universe by considering them as one-dimensional strings that vibrate at different frequencies. This theory is still considered as a work in progress, as there are still many unanswered questions about the nature of the universe. The string theory is a fascinating concept that is known to model the smallest particles in the universe. String theory has been proposed as a theory of everything in physics that unifies all four fundamental forces of nature. However, the mathematical complexities of string field theory in physics make it one of the most challenging theoretical physics models to test. At the heart of string theory are the string fields. These are mathematical expressions that describe the behavior of the strings. The strings have an infinite number of possible vibration patterns, and the string fields capture the properties of these vibrations. String field theory is a mathematical framework that extends the field theory of point particles to the field theory of one-dimensional strings. The string field theory is a quantum field theory of strings, and it is one of the most complex mathematical models in physics. It is so complex that no one has been able to solve the string field theory equation explicitly. The theory has been developed based on perturbative techniques in which the string fields are represented as a sum of simpler fields. The equations of the theory are then solved iteratively. One of the most significant mathematical complexities of string theory is the infinite number of string modes. The string field theory requires the inclusion of an infinite number of string modes. This makes the theory a formidable mathematical challenge. The equations of the theory must be solved for each string mode, and the process is complicated by the fact that the string modes are not independent. They are coupled together, and the coupling is not well defined. Another mathematical complexity of string theory is the presence of divergent integrals. These integrals arise in the calculations of the string theory amplitudes. The divergences are related to the fact that the string fields are non-local in nature. This makes the calculations of the string theory amplitudes very challenging. The presence of divergent integrals has led to the development of various techniques to regulate the integrals, including the use of dimensional regularization and the introduction of counter terms. In addition to the mathematical complexities, string field theory in physics is also challenging experimentally. The string theory makes predictions about the nature of the universe at the smallest scales. However, the energy required to test the predictions is far beyond the reach of current experimental technology. This means that the string theory remains a purely theoretical concept, and the field is still in the process of developing the mathematical tools required to test the theory. In conclusion, the mathematical complexities of string field theory in physics make it one of the most challenging theoretical physics models to test. The theory is based on the behavior of strings, which are described by mathematical expressions called string fields. The theory has an infinite number of string modes, and the presence of divergent integrals adds to the complexity of the equations. The theory is still considered as a work in progress, and the field is still in the process of developing the mathematical tools required to test the theory experimentally.